In a general problem, we have two hoops, wheels, whatever, rotating about a common axis. Now they're not necessarily attached to the same axle. They're rotating about the axis, could be at different rates, they could be accelerating at different rates, and we don't know where they are at the t=0 time, for example. So we would need that information, but the general case is these are both rotating about the same axis, and we're going to call that axis the z-axis. We're going to have an x-axis here for reference, and the origin is going to be at the center of this disk. The y-axis, of course, comes up perpendicular to both the x and the z-axis. So there's a picture of how these things are oriented in space, and they're separated by distance s, so that the center of this rotating object, this wheel, hoop, whatever it is at z-coordinate -s. If the z-axis is in this direction, the origin's here, and this distance is s, then this position is at z equals -s, and at x equals 0 and y equals 0 since it's on the z-axis. Okay, so now we're going to assume angular accelerations, alpha 1 here and alpha 2 here. We're going to assume radii r1 and r2. That might be a little hard to read, but that's what it says, r1 and r2. Now we want a general expression for the position of each wheel. Okay. Now, alpha 1 and alpha 2 are said to be constants. We have constant angular acceleration, so by a couple of integrations we find that the angular position is a quadratic function of time, with the coefficient of t squared being 1/2 the acceleration. That's very straightforward. We've done that integration a number of times. I don't need to belabor that. So in this one, of course, the acceleration is going to be alpha 1, and on this one it's going to be alpha 2. This wheel 1, theta 1 is the position of wheel 1, theta 2 is the position of wheel 2. And theta 1 and theta 2 are functions, of course, of time. Then we have, for each function, two integration constants, b1 and c1, and we know how those arise, so I'm not going to discuss that again. Now, if we know enough information about the positions and or velocities of the wheel, for example, if we know the velocities at two different times, or let's say we know a velocity at one time, a position at some time, okay? If we know the position at some time, then set theta 1 of t equal to that position, and plug in that value for the time, and if we happen to know b1, we can get c1. Similarly, if we happen to know b2, we can get c2. If we happen to know a velocity, we can find b1 and b2. So our velocities, our angular velocities, are just these, and we understand that these are just the derivatives of these. So if we know a velocity of each wheel at some time, we plug in that time, we plug in that angular velocity, and we get b1. Plug in whatever time we know here and whatever angular velocity here, we get b2. So if we know b1 and b2, then if we know two positions, we get c1 and c2. We can also do it with other types of information, but that's a typical type of information we often see. Okay, now, so all I'm saying here is what we already know from studying uniformly accelerated motion. If we know the angular acceleration and have enough information about velocities and positions at specific times, we can get these functions. So let's assume that we've done that. Okay, this is a general case. Okay, any case that we have where the angular accelerations are constant, it's going to look like this, and we just have to worry about getting these constants. Okay, so in general, those are the functions for our positions. Now, what's the relative angular position? As we've discussed, if you're driving down the road and another car passes you, if you consider your direction of motion to be positive, then that car is moving at a positive velocity with respect to you. And that positive velocity is his velocity minus your velocity. If he's doing 70 miles an hour, you're doing 60, he's moving past you at a relative velocity of 10 miles an hour. If he runs into the back of you, he's going to hit you just as hard as he would if you were sitting still and he was going 10 miles an hour. Consequences might be more serious if you're moving down the highway at those speeds, but the impact is going to be the same. Okay, so we understand relative velocity, I hope. So the relative position of wheel 2 with respect to wheel 1 turns out then is just the angular position of wheel 2 minus the angular position of wheel 1. Just like his velocity relative to you is his speed on the road minus your speed on the road. Completely analogous. And then we have relative velocities, and the relative velocity, very similar, would be his minus yours. Okay? So the relative velocity of wheel 2 with respect to wheel 1 is omega 2 minus omega 1. So if the angular positions happen to be theta 1 and theta 2, then we pose the question of how far apart are 2 points on the rim. Okay? You have a point on the rim here at angle theta 1 on the first wheel. What's its position in space? Well, position in space relative to the x, y, z coordinate system, just by the circular model in the xy plane, you know that you're at angle theta 1, which means that your x coordinate is going to be r1 times the cosine of theta 1, and your y coordinate is going to be r1 times the sine of theta 1. Your z position, you're in the plane perpendicular to the z-axis, and your center is at the origin, that you are always, every bit of your wheel is in the plane of the xy plane perpendicular to z-axis, with z equals 0. So z is 0 everywhere on this wheel. So that if the position, x position is x1, y position is y1, then your position vector would be, well, x1 cosine theta 1 times your I vector being the unit vector in the x direction, plus r1 sine theta 1 j, and that j looks like a subscript, I should have written it higher, but it's r1 sine theta 1 multiplied by j vector, and maybe I can fix that a little bit. I get a monstrous j vector here, but there it is, and maybe even parentheses around the sine of theta 1. Okay, so there's your position vector. And there's 0k component because, again, you're in the xy plane, z is 0. So we're going to call that vector r1, that's the position vector for this point. So now here's your vector r1, and it gives you the position of this point. And we could express r1 in any number of ways. I'm going to do it as an ordered triple. r1 cosine theta 1, r1 sine theta 1, 0, corresponding to r1 cosine theta 1 I, that's the x component. Okay, here's your y component, your z component is 0. And I wrote that out here too, but it's easier to read up here. Okay, so your r1 vector now is a vector from the origin out to the position on this wheel. And this is all a function of time. Because remember, theta 1 is a function. Theta 1 is a function of time. Okay. Now for wheel 2, what's your position vector? Well, on the wheel, you're going to be at r2 cosine theta 2i plus r2, not r1, r2 sine theta 2j. But you're also now, you're no longer in the plane, in the xy plane. You're no longer in the plane where z equals 0, you're in the plane where z equals negative s. So at any point on the rim of this wheel, or any point on the wheel, your z coordinate is negative s. So we're going to have a negative sk. So there's the x and the y component by the circular model, and there's your z component. And we could write that vector as r2 cosine theta 2, r2 sine theta 2, negative s. What's the relative position? Well, it's no different than it ever was in the sense that you subtract the position of the point on this wheel from the position of the point on this wheel. So if this is the position on this wheel, and this is your position on this wheel, okay, then the relative position is this vector. Relative position, the vector from here to here. What's the distance from here to here? Well, it's just the length of that vector. What's the length of that vector? Well, it's the square root of the dot product of that vector with itself, by the definition of a length of a vector in Euclidean space. Now, you could go to Pythagorean theorem also. You could subtract this from this, square that, subtract this from this, square that, subtract the 0 from the negative s, square that, add them up, take the square root. You get the same thing. I like the dot product definition because it's really something that's quite useful in physics. Okay, but if you want to use the Pythagorean theorem, square the difference in the x positions, square the difference in the y positions, square the difference in the z positions, and add them up. It works just as well. Another thing on the paper I handed out, I will write, when I'm typing this, it's convenient to write I Beck, and then to do a search and replace to make that into a bold-faced I. So if there's an I Beck that I haven't changed to I, you still read that as just the I vector, and you can cross out the I Vec and write out an I vector if you want, or just cross out the Vec and put an arrow over the I, whatever works for you. Okay? So, this is a fairly complicated motion. It can be very complicated, very difficult to see and understand, but it's really, if you understand everything we've done so far, pretty straightforward to write out the vector for the relative position by writing out the vector for the position of each point and then subtracting them to get the vector that's the relative position. And then you get your distance, and then you can ask yourself, okay, at this time, what's the distance? You could ask yourself, what's the minimum distance? When does the minimum distance occur? You'd have to write those out as equations, and that's a little bit challenging at this point, but it's worth thinking about.